Hi, welcome to lecture 25 of Quantum Physics for Non-Physicists. Today is Wednesday, the 9th of December, and I'm doing this lecture because I owe you a few minutes in lectures, so I've counted and it accumulates to about 110 minutes. So I'll start today, and these are things that you don't need to follow, for example, the tutorial tomorrow. Okay, so it doesn't matter if you watch this a bit out of order. So we had done the Lindblad equations in the last lecture, which allowed us to look at dynamics of open systems. And today we'll look at a specific example for thermalization, and then we'll see an application to heat engines. And the analogy I want to bring to you today is about our relationship to math, because many of you also asked me that they cannot really see the connection between the maths they do, or the mathematical solution, and the physics. And the analogy here is this kind of games. I don't know if you've seen them, where the game itself is this kind of a grid where you can put cogwheels in different places, and your goal will be to kind of make a chain of cogwheels such that if you start moving one, then all of them will move. So for example, here in this case, we have to take this red one and put it somewhere there. Yeah. So that now if we started moving, for example, here the little gray one, then it would move this one, and then it would move that one. Okay. And this is kind of the way we look at math, at least in today's lecture. You know, sometimes it could be that no cogwheel does what you want to do, and you need to develop a new form of cogwheel or invent new maths to solve your problems. But today, the math that we're going to use is really just basic linear algebra and basic differential equations. And I don't want you to think too much or stress too much about whether you're good at maths or not for this. So think of the physics part as being like placing the cogwheels in place, and then the maths part being just turning them, and they do their thing. Okay, so in particular, we're going to find this a system of linear differential equations, and then the maths part will be to just solve them. And I don't care how you solve them. So if you want to use, I don't know, Wolfram alpha or just Mathematica in general, or whatever, a book of differential equations, or if you want to do them by hand, do whatever you want in order to do it, right? I don't care how you turn the wheels. The problems that will appear in the exam, the maths part itself will be relatively simple, or you'll get enough tips for this. What matters to me is that we find a procedure to like put the cogwheels in the right place, okay? The physics part of it. All right, so let's see at the end of today how many minutes we have left. And let's just recap what we did in the last lecture. So we looked at open systems, in particular when we had like a small system of interest in contact with a large environment, which sometimes we call the bath. And the idea here is that the global Hamiltonian, so together they're isolated, but the environment is much larger than the system. That's the dimensions of the two Hilbert spaces. And the global Hamiltonian will be something in the system and something in environment and some interaction Hamiltonian. And then the assumption that we need to do this treatment that we'll do is that the dynamics inside the environment, inside this bath, are much, much faster than this interaction, which means that if my small system gets entangled with a bath, so let me draw here. So for example, this is the bath, and this is my small system here. And if there's entanglement forming between the two at some point, so this is like these two particles, because of the interaction between the two, then these particles become entangled, but these particles move away in the environment fast enough, then it is like the system is always interacting with new particles from the environment, right? And I say particles, it doesn't need to be particles that are actually moving like in a gas. It could also be in a solid, for example, in a metal, that is just that the metal is so conducting that whatever interaction it has with a small system, these interactions are dissipated very quickly. Okay? So if we have this, then we derive this equation, which is a generalization of the Schrödinger equation for density matrices, where we also have kind of an effective action of the environment in my system. Okay, and for this, we don't need to know the initial state of the environment. We just need some kind of heuristics, which will be in the form of some operators. So let's just look at what it was. So the equation is like the derivative of the density matrix of the system is given by this part, which we saw is just straightforward generalization of the Schrödinger equation to the two density matrices. So this is just the internal dimension of the system. This is the Hamiltonian of my small system. And then it has this part, okay? And this part will model the interaction with the environment. Sometimes we call it a dissipator. And of course, this is the part that depends on the path, but instead of having like the global Hamiltonian here, we just have these operators LK, okay, where here we have the anticommutator of the sum of all these LKs with the density matrix, and here we have kind of a cross operator decomposition of a channel. Okay. All right, and these operators, we call them the Lin Blood Operators, and these are the ones that determine how much or in what way the environment affects the system. We saw one very, very simple example, which was kind of the erasure of a qubit, where we just had one qubit with no Hamiltonian, like a degenerate Hamiltonian, and we took only one Lindblad operator. Okay, and we saw that what this Lindblad operator did was to kind of promote this transition from 1 to 0. So no matter what the initial state was of the density matrix, it could have been some rho 0, 0, rho 0, 1, rho 1, 0, and rho 1, 1. It then, at time t, if we plug this into the previous equation, it gave us this. And for time going to infinity, so if we wait a very, very long time, then all of these terms are 0. So it becomes only the state 0 here. Yeah. And today we want to look at a more complicated example. So now we want to have a qubit that has a non-degenerate Hamiltonian. And this will be our first step. So there it is. So the Hamiltonian, we can put the energy of this to 0. It's just a rescaling, right? And the energy of 1 to be some epsilon. And now we want to find the dynamics that give us an interaction with an environment that's a bath that thermalizes the system. So what I mean by this is really think that I want, in the limit of time going to infinity, this state in my system to be the thermal state independently of the initial state of my system. Yeah? And so the goal is going to be finding this, what are Lindblad operators that achieve this, and then like really solve everything and find the expression for rho of time, and seeing that for very large time it really converges to this. Yeah. Good. And then once we have this, then we can model coupling to any heat path of any temperature for a qubit at least. Okay, so in particular, we can think of this application to the heat engine that we've seen a few times now, where we never had an explicit model of how to couple a qubit to a hot bath and a qubit to a cold bath. But now if we have these operators, then we can write the full Lindblad equation for the full system, where we'll just add these operators, LK acting in this qubit and this LK cold acting on this qubit for different temperatures, right? And then we also have the whole Hamiltonian, which is just the basic Hamiltonian plus the interaction Hamiltonian that we saw a few times. And this gives us the Lindblad equation for the whole system, which means that we can really compute the dynamics of the heat engine properly. Okay. So I don't know if we'll do this part in today's lecture, but we'll finish this part here. Okay. So let's start. So we want this thermalization of a qubit, and what we know, well, we know that the Hamiltonian is just this, as we saw, and we know from the simple example that we saw before, so this example of erasure, here we had only one Lindblad operator, and you saw that this Lindblad operator promoted this transition, promoted this final state being 0. Okay? So we're going to guess, and this is not a very particularly wild guess, so I'll not put Sherlock's picture here, but let's guess that maybe if we have L1, this is our guess. If we have the opposite one, this should promote the opposite transition, right? Just by symmetry. If we have, so if we don't have this and we have just this, we know what happens in the case where the Hamiltonian was 0. If we have just this, then we also know what happens, because just by symmetry, if the Hamiltonian is 0, then it's exactly the same problem, just relabeling the states, right? Then we know that we should end up in state 1. So now let's just, as a guess, let's take a little bit of this and a little bit of that, by which I mean, well, let's put some coefficients here, alpha and beta, and we will we'll determine what they are later. Okay. So this is kind of our guess. And now we can write the Lin Blood operator equation with this. So let's get the Lin Blood equation. True. Okay. And now let's just take care of each of the terms at hand. So let's say we have 3 terms here. Delete this. So we have that term, this term, that's number 2, and let's say the blue term. Oh, I copied it to the wrong place, sorry. Okay. So here's our 3 terms. So let's call this 1, 2, and 3. And now arrives the part where, well, we already have our guess, and now comes the cogwheels. Okay, so now we plug in our guess into here. We're going to see what matrix we end up with on this side of the equation. Okay, now we have all the LKs. We have some guess for the initial state or for the state at a time t. We can keep it completely general, so we'll just compute what this has. And then at the end, we'll end up with a differential equation with this on one side and that on the other. We plug in everything again, we solve this differential equation, and then we'll still have this freedom of choosing these alpha and betas and some coefficients that will show up later. And to solve this, then we'll just see the limit cases. And the limit cases are, well, at time equals 0, we know what the state is that we wanted, it's the original state. And at time equals infinity, we know that we want the thermal state. And this will be enough to kind of fix all these parameters in a physically meaningful way. Okay, so now we need to solve all of this. So let's start with number 1. Okay. Number 1. So what is HS? So let's just do this. So we have epsilon over I H bar, because HS was just 1, 1, right? And then we have here rho S of t. There we go. So we have this to solve. Okay. A, and then what is this? So this matrix is this matrix. So because it's a qubit, it's easy to do it in matrix form. This will not always be the case. So here, I always write the coefficients that depend on time, if I remember. Like this in green, sorry, in purple. So this is our density matrix at a time t. Okay. Minus. So if you know how to solve this, which I'd expect you to, feel free to skip now the next few minutes. Okay. So this gives us the matrix 0, 0, and now this. Minus the matrix 0, 0. Okay. And if you're not too sure, you can stop to solve it on your own. So that is epsilon over IH bar. And the matrix you get is 0, 0, and here minus, minus rho 0, 1 of t, and here rho 1, 0 of t. Okay, so this was part number 1. What's part number 2? What's this? Okay, with the minus sign and all. And what are this? Our guesses are this. Let's just bring them for our Lin Blood Operators. Zero, and this is a 1. Okay. So what is the sum over LK? Check, check. LK dagger LK. So this is going to be alpha squared. And now here, 1, 0, 0, 1 plus beta square. And now 0, 1. So that's the complex transpose of this. Transpose conjugate 1, 0. Right. This is 1. And this is also 1. So we have this alpha square 1, 1 plus beta square 0, 0. So this is a matrix. In matrix form, it looks like this. And now, just for simplicity, so we don't have to write the squares all the time, let's just call x this alpha square, and y is going to be this beta square. Okay. I'll just write the notation. And this is really just for simplicity so that we don't have to write all these things all the time. Okay. But what we need to do is to do this minus 1/2 of sum over k. Okay. Okay. So S over time t. So that's what? Okay, it's going to be minus 1 over 2, and here we have y x 0, 0. And now comes our matrix at time t. Let's get it. So we don't have to write it all the time. Check. Plus the other term, so minus 1/2 matrix. And the other matrix. Okay. Now, sorry, let me try to make this a bit more. Need and hidden away. Okay. So now we just have to sum these two matrices. And this gives us the following. Well, I mean, we have to multiply them, then I have to sum them. And I'm going to ask you to trust me on this. So this is going to give minus, and then this big thing that I'm about to write. So it's going to be y rho 0, 0 of t. And now here, x plus y over 2 rho 0, 1 of t. That's going to be something times rho 1, 0 of t. And there's going to be something times rho 1, 1 of t. And these somethings are x, and here again, x plus y over 2. Okay. And you can compute this very easily if you just multiply these matrices and then sum them. Okay, so this was term number 2. Let's go to term number 3. There it is. Okay. So what is this? Sum over k, lk, os of t, lk dagger. Okay, so let's start with the L0. The first with L0 is going to give us alpha square, and then 0, 1, os of t 1, 0, plus beta squared 1, 0, os of t 0, 1. Okay, so I can just bring back what these two operators were. Okay, so they were this. So we have that. So alpha squared we called x. So we have x, the state is 0, 0, and then there's another coefficient here, which is 1 rho s of t 1. But if you look at rho s of t, right, this is the matrix. If you kind of pinch it with 1, 1, the only term that survives is this one here. So this is rho 1, 1 of t. Plus y 1, 1 times this number, which is not hard to guess. This is going to be just rho 0, 0 t. Okay. So what is this? Let's put it all in a matrix form. So first we have this term, which is 0, 0, so it's going to come here. And it has this coefficient. So it's going to be x times rho 1, 1 of t, except this depends on time, so I should make it purple. Okay. And down here we have y, so it's the term 1, 1, so it comes here. So it's y rho 0, 0 of t, and nothing in the off-diagonal terms. Okay, good. So now we have 1, 2, and 3. So let's get the Lindblad equation again. Okay. And now we just get the solutions for each of these terms. So the solution for number 1 was this. And now the solution for number 2 was this thing here. Yep. Nice, very good. And the solution for number 3 was this thing here. Okay. So there we are. Now we just have to sum all these matrices. And it might be a bit easier to write, oops, sorry. It might be a bit easier to write this as minus I, because then it will be simpler to do. So just looking at this, the nice thing is that in the off-diagonal terms, it's always the same coefficient that depends on time. Right, so this is the original there, and there's nothing here. This is the same there. So what we have overall, we have first here minus this. In the first one. Okay. For the second one, we have this thing. Multiplied by minus I epsilon over h bar, and you have x plus y over 2. Okay. Here we have oh, sorry, this is plus because there's a minus up there. So here we have minus I epsilon h bar, x plus y over 2 times this thing. And finally, down here we have this. Maybe I can like this. Minus that. Okay. And let me just make it even a bit more obvious where the separation between terms is. Okay, very good. So what have we achieved? So far, this was just cranking the cogwheels. So on the left-hand side, we have the time derivative of something, and the right-hand side, we have this result. And this gives us a system of differential equations, okay? Of which there are many ways to solve it, and do not discount just typing it into Mathematica and solving it. I will do it kind of by hand here, so we can see sort of how it works. But again, how you solve it, it's not so important. Okay. Okay. So this is equal to what's on the left side. By the way, this is d dt of, well, of precisely just the density matrix at time t of this thing here. Okay. So essentially, we have 4 differential equations, and they're all relatively easy to solve. And I'll show you just one way of doing it. So d dt of rho 0 t zero 1 1 0 1 1. Let me just copy what we have here. So there you go, this for the first term. We got this for the second term. Oh, oops. There we go. The third one. Is this? And the last one is this. Okay. So just looking at this, the first thing we can notice is that, well, the 2 middle ones, these are kind of independent of everyone else. So like this one only depends on the row 0 1, and this one only depends on the row 1 0. Okay. So I'm going to solve these equations. Let me give you numbers: 1, 2, 3, 4. And these two can be solved independently, whereas these two kind of depend on each other as coefficients. And of course, I could solve everything like a big system of linear differential equations, and this is really a matter of personal taste and what tools you're used to. But for me, I prefer solving a smaller system of linear differential equations and solve these two on their own, especially because they're kind of direct. Okay, so let's do 2, for example. Well, this is really just what's the thing such that the derivative is the original function times the coefficient. Okay, and that's just exponential. Right, so for 2 the solution I get is rho 0, 1 of t. It's going to be the exponential of t times this thing here. Times some coefficient here, c. And how do we determine this coefficient c? Well, we know that rho 0, 1 of time equals 0. This is the original density matrix. Okay, so we just call this rho 0, 1. So then time equals 0 means that this whole thing would be 0. So then this is just c. Okay. So t equals 0, we want this. So this is where the physics comes in, right? We want it to be the initial density matrix of the system. Okay. So then this gives us rho 0, 1. Can make it in purple. Rho 0, 1 of t is this thing times rho 0, 0, 0, 1, which is the original coefficient in density matrix. And another thing we can do is what happens when time goes to infinity. Well, then, oh, sorry. I missed a minus somewhere on the way, so this should be minus, and this should be minus here. Let's see where I missed it. So this should be minus, and this should be a minus there. So minus this whole thing. Okay. Where did I miss it? It was just here when I summed up this. This should be a minus there. Yes, I forgot this sign, this minus sign there. Okay, good. So at time going to infinity, so this is minus this, and I can split this terms in, maybe it's easier to see this if I split it into 2. So look, here x and y are both positive. This is larger than 0. And we know this because x and y were like this absolute values of alpha and beta, right? They were alpha squared, alpha modulo squared, b squared. This thing, this term here is periodic, right? So it has a real and imaginary part that both are periodic, but they're very bounded. But this term here, it decays exponentially, right? Okay. So as time goes to infinity, then this thing goes to 0. This is bounded by 1. This is a constant, so the whole thing goes to 0. And again, if you don't see this immediately, just plot it, right? You can just go to your favorite program, plot this. You can plot the real part plus the imaginary part, and you see that both of them go to 0 at time goes to infinity. Like intuition just comes from doing something many, many times. And in particular, intuition for this. Yeah, physicist intuition for mathematical functions comes from plotting them many, many times. So just do it. So number 3 is very similar. So now we want rho 1, 0 of t. And the only difference was this sign here was minus. And again, we wanted that at time 0. This is 1, 0. So this coefficient becomes 0. So we get this coefficient is rho 1, 0. And here there's a minus sign. That's the only difference. Okay, so that's There's minus sign here, that's important. Okay. So again, it also goes to 0, which is what we wanted, right? Because remember that we want that in the limit of large T, my density matrix goes to the thermal state. And what's the thermal state? So maybe I should have written here the goal. I need that rho s of time equals 0. This should be some arbitrary initial state. But when time goes to infinity, I wanted to thermalize to the thermal state, which is 1 over z, 1 e to minus this constant, this Boltzmann constant, Kb. Epsilon is the energy gap divided by the temperature, right? So in particular, I need this off-diagonal terms to be 0, which is what we just achieved here, right? This, the top right term goes to 0 and the top left term goes to 0. Perfect. So now we have number 1 and number 3 to solve. So let's just get them. Okay. Oh, not number 3, sorry. No. I wanted number 4. And now again, there's many ways of solving this system of differential equations. And the way I went about it is probably not the neatest, but it was just by just saying, well, let's say this x of t, I'm just going to call this x of t a vector. This is going to be my rho 0, 0 of t, rho 1, 1 of t. Okay. I'm not doing anything. I'm just putting this, taking these two variables and arranging them in a vector like this. Okay, it's not normalized in particular because we know that the sum of them adds up to 1, which is not a normalization condition for vectors in Hilbert spaces, but it's just a vector. Okay, don't think of it as a cat, just a vector. Okay, and then this whole equation, so the system of equations can be written as dt of x of t equals matrix times x of t again. And this matrix is if I got it right. Yes. Oh, sorry. Minus y x x minus y. Okay. You can see that this is the case because, well, if we just replace if we just replace this here, then you see that they multiply exactly for this, to this thing here. Yeah. Good. And that's even easier to see if I put it like this. Okay. And this is my matrix A. Let's call it A. Okay. So then what I have is a differential equation for a vector. Okay. Which this is now very easy to solve in general. And I'm sure you've done it a few times, but also right here how we can solve this. And of course I could have done this for the system of 4 differential equations, but given that 2 of them were so easy, I thought that this would be simpler. So I'll just write here matrix form. So the solution for these things has several steps. First step 1 is diagonalize this matrix. So if we can write A being the sum I of some eigenvalues times some eigenvectors, then the solution is exactly kind of the same as for the other simple differential equations, which is x of t becomes just sum over I of some ci to lambda I t vi, which is kind of the same in spirit as having just the exponential of the matrix times some x of time 0. Okay. And of course that we can double check. I mean, just to show you that this is the solution. Then we can derive this. And then we get what? Well, we get the sum over I of now this lambda i's, ci e I t vi. But now we can write this in a form that is slightly longer, which is going to be I lambda I vi times the sum with now a different index j cj e to lambda j t vj vj. Okay. Why? Because now when we multiply this and this, you get the delta ij, right? So then we know that this term is the only one. The terms that survive are the ones where I equals j. And this thing here is exactly my matrix A, like we saw before. And this is my x of t, right? So that then this equation is the same as this original equation. Okay. So now we have this task to do of diagonalizing this matrix A. And what's the matrix A? It's this thing here. So, I mean, we can do it by hand. Look, I imagine that everybody knows how to diagonalize a matrix. You can just go to from alpha and write eigenstates of A or eigenvector of A. But just to have the general procedure written somewhere somehow, we can do it by hand here. Okay, so let's do it. So if you remember from linear algebra 1, to find the eigen values first, we need to solve this equation where this is a determinant of this matrix, and these solutions, the lambda solutions, will be our eigenvalues. So in our case, we get minus y minus lambda x, y minus x minus lambda equals 0. And what's the determinant? Of a 2 by 2 matrix, it's this term times this term minus this term times this term. So we can do it by hand. So in the end, we get y plus lambda x plus lambda, because all the minus signs cancel out, minus xy equals 0. And this gives us xy plus lambda x plus y plus lambda equal minus xy equals 0. Check, check. And this gives us two solutions, right? Either this is 0 or this whole thing is 0. So we have two solutions like lambda 0. The first is 0, and the second eigenvalue is going to be minus. That's right. Good. Now with the eigenvalues, we can find the eigenvectors. So for lambda 0 equals 0, now we need to solve the equation A minus lambda 1 identity times my v1, my first eigenvector. This has to be 0. Okay. Lambda 1 is 0, so we get just A minus y x y minus x times, well, this v1, I can write it as, there's two terms, v1. These are the two terms, and this needs to be 0, 0. Okay. Well, sorry, let's call this v0. V0, v0. So this tells me that v0, we can solve this by hand, but this gives in the end that v0 is x, y, up to now normalization, which could be anything. Okay, but we don't care about this for now. So it's proportional to xy, so this, for example, will solve it. Okay, good. Let's do it for the other eigenvalue. So we have lambda 1 equals minus x plus y. So then we have this equation to solve. So A minus identity. This is almost like an extra tutorial. V1, this should be 0. And this means that what we get here, it's going to be, overall, is going to be x, lambda 1, y times now my v1, 0, v1 equals 0. Okay. And now what's the vector that makes this work out? Well, if you multiply them, then you'll see that your v1 is essentially the minus vector. So it's 1 minus 1 up to normalization. Okay. Okay. Good. So now what we have left to do? Oh, we were just diagonalizing A, so our solution is that A equals 0 times that vector there, x, y, plus minus x plus y times this vector here. Very good. Now, we'll get our solution, right? Yeah. And again, this is just moving the cogwheel, so please feel free to skip if you don't want to go through it. So this is, let me just remind you of what this x of t was. So this was the rho 0, 0 of time and the rho 1, 1 at a given time. This is now some C0 that we don't know yet, e to 0 times, so that's just 1. And now V1, so x, y, plus some C1 that we don't know yet, e to minus x plus y time. Whoop, I forgot the next sign. 1 minus 1. Okay. So we still have these two free parameters, C0 and C1, that we don't know what they are yet. But we'll get there. This here is nothing. So let me just write what the full density matrix looks like at this point. Okay, so we have that rho of at a time t, which is this rho 0, 0 of time, rho 0, 1 at time t, rho 1, 0 at time t, rho 1, 1 at time t. This looks like what so far? Well, yeah, we have to solve this. Sorry, we have to solve this a bit more before we can do that. So let me just write what this is. So this is C0x plus C1 e2 minus x plus y t on top, chook. And here's C0y minus C1 e2 minus x plus y t. Okay, there we go. Okay, so all I did here was really to just put this inside this vector and then summing these two vectors. Good, so let us plug everything in. We have this here. We have this in the other corner because this corresponded to rho 1, 1, remember? We were looking at rho 1, 1. That's this thing here. And then in the off-diagonal terms, what do they have? We have this. This one belongs here. Make it a bit smaller. Okay. And there's only one left, which is this one for the editor. Okay. So now comes the part of being a physicist again. We have a few things to work out. So we have to work out what x and y are. So these were the coefficients in the Lin Blood operators, if you remember. And we need to work out what this C0 and C1 are. Okay. So then let's just look first at the limit of when t goes to infinity. So when t goes to infinity, then what we have here? Then we have rho of t going to infinity. This is what? Oh, look. Here, this goes away, right? Because it's time. This term goes away, this goes away. We've already seen here. And this two stay. So we get C0x and C0y. 0, 0, okay. Good. And we want this to be 1 over z, 1 e2 minus, was it epsilon k over t? Right, we want this to be the thermal state. This thermal state for this Hamiltonian temperature T. And this gives us an idea, so let's just say, well, let's set then the following. For example, we can have x equals 1, y equals e2 minus epsilon k over t, and c0 equals 1 over z, which is 1 over 1 plus epsilon k over t, which is 1 over x plus y. Okay. So as you see, there's some freedom here. And the freedom is that we could scale up x and y and then just scale C0 accordingly, right? So there could be some alpha here. Oh, alpha we used already. So some gamma, as long as you put here 1 over gamma, then everything works out. And such constants gamma will just tell you how fast this thermalization happens in the end. Okay, but for now we don't have to worry much about this because we can make an arbitrary choice. But just remember that we could change these coefficients here by a little bit. As long as their ratio is still this kind of ratio of the thermal state, then everything works out. Good. So we did that. So now let's just rewrite this thing again. So now we have that rho of t equals what? Equals this thing. Good. Where now we can already start replacing this things here. So x0, x, this was just 1 over z. And this was e2. Oh, did I forget a minus? No, I did not. I forgot a minus here. E2 minus epsilon k over t for z. And wherever there's x plus y, that's 1 over z as well, right? So I can replace it there as t over z. That's t over 2z. That's t over 2z. And that's t over z. So by the way, this reminds us a bit of what happened in this very, very simple example that we saw last time. So I'll tell you to look at something here, and then I'll show you in the other one. So remember here these coefficients, that here you go with some factor over 2, and here you just go with the factor without the over 2 there and there. And if you look a long time ago, when we first looked at this simplest example, we had the same behavior here. So here it was the initial factor, and then it decreased exponential with this factor that was something over 2, and here without the over 2, right? Good. Okay. What we still have to fix? We still have to fix this C1. And for this, we'll look at what happens at time equals 0. So there we have rho of t is 1 over z plus C1. Here we get rho 0, 1 as we wanted. Here we get rho 1, 0. And here we get E2 minus epsilon k over t over z minus C1. Okay. And what's the goal? Well, we want this thing to be rho 0, 0. And we want this thing here to be rho 1, 1, which by normalization of the initial density matrix, this should be just 1 minus rho 0, 0. Okay. So we have simply that 1 over z plus C1 should be rho 0, 0. So C1 equals rho 0, 0 minus 1 over z, which is the same. So you could do the same analysis with this term instead. And you can see that you can also write C1 as rho 1, 1 minus E minus k t z. And this is true because, because you can replace rho 1, 1 with 1 minus rho 0, 0. And this 1, you can write it as z over z. And then z, you know that it's 1 minus this. So it all works out and you end up with the same solution. Okay. But we don't have, you can do this at home if you want. Good. So, conclusions. We have that our Lindblad equation, Lin Blood Operators. We had L0, so this was alpha 0, 1, and our alpha square is 1, so it was our x, that's 1, so that's just 0, 1. And L1 was beta 1, 0, and this is square root of x, so it's going to be e to minus k over t epsilon over 2, 1, 0. And note that we can, in principle, multiply them by the same factor, top and bottom, because this will just correspond to a faster thermalization, so faster or slower thermalization, depending on the value of this factor. And then what we have to do if we do this is to then adapt the value of C1. Okay, but for now, if we put this to B1, everything should still work out. So with this, we have that time evolution. Ooh, okay. Let's copy this whole thing. So we have rho of t equals, and now this C1 and C2 we can replace. So we have there's many ways in which you can group these things, but let's just group it in the way we did it so far. So rho 0, 0 minus 1 over z times this. And here, rho 1, 1 minus e to minus epsilon k t over z. Okay. So, and again, if we change the, if we change these lambdas, if we add some lambdas here, I think we'll see the effect mostly here in the coefficients that tell us how fast. Yeah, it's going to be lambda squares here, not lambdas, but you'll see. That tell us how fast this kind of decoherence happens. I call it decoherence because what happens is that the off-diagonal terms go to 0, so you end up with a diagonal matrix. So you lose the coherence between basis elements. So the fact that we have superpositions becomes just a mixture. And yeah, and we have this thermalization. Good, okay. So then we can write this in the whole, we could write the whole Lindblad equation again with this. And now the next step, which we'll do next time, it's going to be indeed to now look at the heat engine. So now we have the Lindblad equations for, so the Lindblad operators for the hot qubit, the cold qubit, they're going to be exactly the same, but with a different temperature. And of course, that there's going to be like 0, 1 tensor identity in the rest, right? So in the hot, for example, times identity in the rest, and so on. And then we can write the Lindblad equation of the whole thing, right? Together with this and so on. And then we can see, we can look at the time evolution of the whole system of battery, hot qubit and cold qubit. And then we can compute exactly the efficiency and also the power of this engine and so on. Okay. So that's a lot more of cranking up to do. So I'll leave this for the next lecture.